Welcome to Math, where problems are no problem. Ever stared at a circle covered in angles and had no clue which theorem to use? By the end of this video, you'll be able to look at a circle diagram and instantly know which rule applies. We're going to use just one circle, one set of numbers, and build up four major circle theorems, one on top of the other, so you see how they all connect. First, some vocabulary. The center of the circle is a point called O. A line from the center to the edge is a radius. A line connecting 2 points on the circle is a chord. The curved part between 2 points is called an arc. And an angle formed by 2 lines meeting at a point on the circle itself is called an inscribed angle, or an angle at the circumference. Now let's build our example. Mark 2 points, A and B, on the circle, and draw the radii OA and OB plus the chord AB. Let's say the angle at the center, angle AOB, measures 80 degrees. Next, pick a third point, C, way over on the far arc, the major arc, and draw lines from C to A and from C to B. This creates angle ACB, an inscribed angle sitting on the same arc as our central angle. Here's theorem number 1. The angle at the center is always twice the angle at the circumference, when both stand on the same arc. Since OA, OC, and OB are all radii, they're equal in length, which makes triangles OAC and OBC isosceles. That equal-sided setup is exactly what forces the doubling relationship every single time. So angle ACB equals 80 divided by 2, which is 40 degrees. Now let's add a fourth point, D, also on that same major arc, and draw lines DA and DB. This gives us angle ADB. Here's theorem number 2. Angles in the same segment are equal. Since C and D are both on the major arc, looking at the same chord, AB, they both use the exact same central angle to find their value. So angle ADB is also 40 degrees, exactly matching angle ACB. Now, a special case. What happens if AB isn't just any chord, but a diameter, a straight line through the center? Then the central angle AOB isn't 80 degrees anymore. It's a straight line, 180 degrees. Using the exact same rule from Theorem 1, the inscribed angle would be 180 divided by 2, which is 90 degrees. This is theorem number 3. The angle in a semicircle is always a right angle. Any point you pick on the circle, if you connect it to both ends of a diameter, gives you a perfect right angle. Let's go back to our original circle with the 80-degree central angle, and add one more point, E, but this time on the short arc, the minor arc, on the opposite side of chord AB from C and D. Connect E to A and E to B. Now connect the 4 points A, D, B, and E in order, forming a four-sided shape inside the circle, a cyclic quadrilateral. To find angle AEB, we use the reflex angle at the center, the bigger way around, 360 minus 80, which is 280 degrees. Cutting that in half gives us angle AEB equals 140 degrees. Here's theorem number 4. Opposite angles in a cyclic quadrilateral always add up to 180 degrees. Let's check it. Angle ADB is 40 degrees, and angle AEB, directly opposite it in our quadrilateral, is 140 degrees. 40 plus 140 equals 180. It works perfectly. Let's double-check everything ties together. Our central angle was 80. 40 times 2 gives us back 80, confirming theorem 1. Angles C and D both landed on 40, confirming theorem 2. Angles in the same segment. And 40 plus 140 gives 180, confirming theorem 4 for our cyclic quadrilateral. So here's the one idea to remember. Every circle theorem we covered today is really the same relationship in disguise. The angle at the center is always twice the angle at the circumference on the same arc, and that single fact is what makes semicircles give right angles, and cyclic quadrilaterals add to 180. If this helped, the next video covers the alternate segment theorem, using tangent lines instead of chords. If you found this useful, subscribing helps this channel keep making more of these.